Great. So yes, I'm very glad to be here. Thank the organizers for the invitation. So the title changed slightly from what's in the program because I, in addition to talking about the resolvent that's mentioned in the program, which I will, I wanted in the now third part of the talk about some very recent results that tie in very nicely with what Greg has been saying in terms of stratified spaces and so forth. So this is joint work with Pierre Alvin and Greg. And here's the outline. So the first part of the talk will be just kind of some background classical results of Morse theory and sort of Witten's version of Morse theory. Then I'll talk about our construction of the resolvent in this context. And then in the third part, I'll talk about the Morse-Smale complex and sort of thinking of this as a stratified space and sort of some exciting journeys there. All right, so for most of this talk, we're just going to be thinking of a closed manifold. So we've been thinking about stratified spaces, but the results that I'm going to mention are just going to be for the case of a closed manifold. And then we hope to sort of extend this method. This is really kind of laying the groundwork to extend this method to stratified spaces in the future. So I'm going to pick a smooth function on my manifold. That's going to be f for the duration of the talk. I'm going to always denote by C the set of critical points of the function on the manifold. And so probably most people here know what a Morse function is, but just to remind you, a Morse function is such that this critical set consists of discrete points, which are isolated from one another. The Hessian of f is required to be non-degenerate at these critical points. So that implies a few things. So first of all, the tangent space at a critical point splits into sort of positive and negative pieces, corresponding to, you could say, eigenvectors for this quadratic form viewed as a matrix. Morse's lemma says that there's a normal form for this function. You can write it near, there's coordinates centered at the critical point, such that the function looks essentially quadratic, negative directions and positive directions. And the index of the critical point is the number of these negative directions, equivalent to the dimension of this negative part of the tangent space. So, obligatory picture here is a sphere, which for dramatic purposes has been presented to you as a hot dog, so that has sort of a more interesting critical structure. So the function that I'm thinking of here is just a height function. So, maybe it's 0 down here and increasing as you go up. So the critical points are as follows. There's an index 0 critical point at the bottom, an index 1 critical point. See, there's a negative direction along here and a positive direction along the saddle, and two index points, two critical points of index 2 at the top. So there's two generalizations of Morse functions that I want to consider. So the first are Morse spot functions. So a function is Morse spot if this critical set is a disjoint union of smooth submanifolds of M. And we require, in this case, that the Hessian be non-degenerate as a quadratic form in the normal directions. So, in this case, again, the normal bundle splits globally as a vector bundle into sub-bundles, which I'm going to call n plus and n minus over the critical set. So, let me mention, these submanifolds might have different dimensions, so I'm going to allow components to have different dimensions. I'm going to refer to the index of a component of the critical set. Again, it's the rank of this vector bundle. There's, again, for the normal form in components, in coordinates rather, in normal directions, the function can be made to look just as before. An example where Morse spot functions arise is if you have a fibration of smooth manifolds and you take a Morse function on the base, well, then you pull it back to the fibers, whatever was a critical point on the base, the corresponding fibers above that point to be Morse spot critical sets. Here's another pictorial example. So a torus lying on its side, lying on the floor. I'm going to again take the height function. So now I have two critical sets at the bottom, an index 0 critical set. And now this is an index 1 critical set because I just have one negative normal direction. And this is an example, this is an example coming from a fibration, because if I consider the product onto a circle factor, right, I'm equivalently looking at the height function on the circle and pulling that back by the product, by the projection onto the product. All right, and then another generalization is what's called a generalized Morse function. So again, here the critical points are points. The critical set is just discrete, isolated points. But we now allow some of the critical points possibly to have a degeneracy of a very certain type called a birth-death critical point. And perhaps the most efficient definition is to just say that there's a normal form for such points where, again, I have this quadratic behavior as before, but now I allow it to be cubic in one of the coordinates. So why do you consider such a thing? Well, so before I get to that, so again, I have a splitting of the tangent bundle. Now I'm going to call T0 this direction in this cubic direction. It's the direction in which the Hessian graph vanishes. So the motivation here is considering families of Morse functions. So say you have a fibration and you want a function on the total space of the fibration that is Morse, or in this case it's going to be generalized Morse along the fibers, and you think of it as smoothly parametrized by the base. So a result of Igusa says that the space of generalized Morse functions is connected, in fact fairly highly connected. If I just restrict to classical Morse functions, two Morse functions, well, the space of Morse functions, you could say, is disconnected, right? In particular, two Morse functions can't be connected by a smooth path of Morse functions unless they have the same number of critical points and same number and type of critical points. And here, so birth-death critical points are what are occurring in a family when two nearby non-degenerate critical points annihilate one another. So here's kind of a picture. So if I think of this thick line as being my manifold, and this is supposed to be the graph of the Morse function over the manifold. So I have two critical points here, whose index differs by 1. And as I deform this function by sort of pulling the ends and straightening it out, these two critical points approach each other, and then at a certain point this looks like approximately a cubic, the first order, and the 2 points become a generalized, or degenerate critical point in this generalized sense. And then after that, I can pull the thing straight and disappear altogether. Great, so I'm going to remind you what the Morse inequalities say. This is a fundamental result of Morse theory. So one actor here is going to be the Poincare polynomial of M, which is just a polynomial whose coefficients are the Betty numbers, the dimensions of the cohomology groups of M with coefficients in some field, always R over V. So I can define another polynomial by taking the coefficients to be, well, let's see, in the classical Morse case, I'm going to take the coefficient mu sub k to be the number of critical points with index k. In the Morse plot case, I'm going to take it to be the dimension of the compactly supported kth degree cohomology of this negative normal bundle. So remember, the normal bundle over the critical point, over the critical set, splits into positive and negative components. And I'm just going to consider the sub-bundle corresponding to the negative directions. Another way to write this is using, this is just the Thom isomorphism here, is this is just the sum over components, critical set components, of the dimension of the cohomology of the components in degree k shifted by the index of the components. And this means the orientation bundle of this negative normal bundle. So if the negative normal bundle is trivial, then this is nothing, this is just R. If the negative normal bundle is not trivialized, then what I mean is this is cohomology with coefficients in a local system described by this orientation. So the Morse inequalities can be stated in this way, that you can compare these two polynomials with an error that factors like this. It factors as 1 minus t times a polynomial with strictly positive coefficients. So if you like, another way to state this, an equivalent way to state this, is that you have inequalities between alternating sums of the Betty numbers over here and these Morse coefficients over here, with equality, so sum up to some level for each k have inequalities like this, and then equality holds when k is the dimension of that. I mean, you can see that here when you just let t equal minus 1, and this is 0 of the polynomial. So let me just state that you get these type of inequalities. These are just an exact algebraic consequence of computing the cohomology with a finite dimensional chain complex. So if I have just some abstract chain complex whose chain spaces are finite dimensional vector spaces, then I can form a polynomial M like this with coefficients, the dimensions of those vector spaces. I want to compare that against the polynomial whose coefficients are the dimensions of the cohomology. In you get exactly these types of inequalities. So another way to say this is, if I give you a chain complex and I don't tell you the differential, what can you say about the cohomology? This is essentially as much as you can say about the cohomology without knowing specifically how the differential acts. So for instance, classically in topology, a Morse function gives the manifold a specific CLU complex structure with one K cell for each critical point of index K. And so if you look at cellular cohomology, then the dimension of the cellular cohomology chain space in K is exactly the number of critical points of index K. So that's a way to prove the Morse inequalities. In this case, once you know that. So now let me introduce Witten's idea of how he sort of understands Morse theory. It's a very beautiful picture. So given a Morse function, and now we're going to take a Riemannian metric on M, and we're going to look at the complex of L2 forms on M. But instead of looking at the ordinary de Rham differential, I'm going to conjugate it by e to the TF. So this is a deformation of this complex by deforming the differential. So this is still the complex d, let me call this thing d sub t, dt squared is still equal to 0, right? Just because these things cancel off, and dt squared is equal to 0. If I expand this out, this just looks like d plus the wedge product with df. Great, so of course when t equals 0, this is the original de Rham complex. And in fact, the complexes are isomorphic. If you multiply all your forms by e to the tf, these two complexes are isomorphic. In particular, their cohomologies agree. I'm going to call h sub t the cohomology of this complex for a fixed t. So, okay, what's the point, if these things are isomorphic? Well, the point is that for each t, Hodge theory applies. So I can form the Hodge-Laplacian for a fixed t, whether it be dt plus dt star squared. And that, we get the whole Hodge theory package for this. This is a nice elliptic operator, self-adjoint. So in particular, it has non-negative discrete spectrum, and moreover, eigenforms form a complete basis for L2. So I'm going to denote by omega sub t lambda the space of let's say k forms, which are eigenvalues of the Laplacian delta t. So for each t, a complete basis for L2. For a fixed lambda, these eigenspaces are preserved IDs. They form subcomplexes, and one way to state, Hodge theory is to say that for positive lambda, you get exact complexes, and for lambda equals 0, you get a trivial complex. And so, in particular, the only contribution to the cohomology comes from the harmonic forms, or the lambda equals 0 in the spectrum. So in particular, we can compute cohomology using any collection of these eigenvalues that contain 0. So, for instance, if I just take an interval and I restrict to eigenforms whose eigenvalues lie in interval 0 to t, as long as that interval contains 0, I get the same cohomology. And now Witten points out that what you get out of this is that for large t, the spectrum does something very interesting. It splits into a large part, we're going to call large eigenvalues, which are going off to infinity asymptotically over t. And then there's a finite number of small eigenvalues which are approaching 0, in fact, exponentially fast. So in particular, for a large enough t, there's a gap that forms here, and I can pick a constant that lies inside this gap, and then if I look at the complex of small eigenvalues, which I can compute by taking a cutoff like this, again, get the same cohomology, but Witten's insight here is that there's exactly one small k-form for each critical point of index k. So in particular, this is a finite dimensional chain space again, and I get the Morse inequalities just from this fact, because I can count these things, they're in bijective correspondence with the critical points. All right, so some history here. This is originally due to a paper of Witten in 1982. Seminal paper is really beautiful because there's a lot of amazing things in there. But it's really a physics paper, and he really sort of computes these things using ideas from quantum field theory. So it's a few more years before there were mathematically rigorous results of this. The first was in 84, 85, a series of papers by Helfer and Schusterman, who using semi-classical techniques. Bismuth gave a probabilistic proof of this in '86. And then there's also been some work in the Morse-Bott case. Again, due to Bismuth, this is the same paper. Also, due to Braverman and Farber, who consider the Novikov inequalities, which are a similar setup where instead of looking at DF, an exact one form, I can just ask for a closed one form and do a similar deformation of the Hodge, do a similar deformation of the Duran. And there have been some results announced in the generalized Morse case. As far as we're aware, no published results. And let me just tell you what the picture is in these generalized cases. So this is the picture in the classical Morse case. In the Morse-Bott case, there are the sort of large eigenvalues, if you like, are actually order 1. They stick around. So I'm sort of inclined to call these medium eigenvalues. But again, you can still distinguish them from the small eigenvalues, which are rapidly approaching 0. And in the generalized Morse case, you expect to see sort of medium-large eigenvalues. There are some things that have asymptotic order t to the 2/3. And what I want to point out in the generalized Morse case is the only contributions you get are from non-degenerate critical points. The small eigenvalues only correspond to non-degenerate critical points. The degenerate critical points are contributing this stuff, which is large. And at a topological level, you can see that you expect the degenerate critical points not to have a contribution to the Morse inequality, because as you flow, if you're considering just the sub-level sets of the manifold and sort of flowing along sub-level sets, as you pass a degenerate critical point, the topological type of the manifold doesn't change, so you don't really expect a contribution. All right, so what are we doing here? Well, our view is the best way to understand the spectrum of the operator is to understand its resolvent, so let's construct the resolvent of this Witten Laplacian. So part of our work is to build a framework here for the construction of this resolvent in sort of a uniform sense. And so from now on, I'm going to switch variables on you. Instead of using t, I'm going to use h, which is 1 over t. And instead of considering the limit as t gets large, I'm considering the limit as h goes to 0. And we'd like to say something uniformly about this operator, and the limit as h goes to 0. And so, while the manifold itself is a perfectly smooth space, if you like, at this point, the singularity in this problem is a singularity in the operator. This operator is becoming singular at h goes to 0. So we want to sort of understand how to deal with that singularity. And the idea is that this framework that we're setting up is going to extend to stratified spaces. And so settings like the manifold cone points, edges, area edges, whatever kind of gear you want to put in there, and we'd like to try to analyze that situation as well. All right, so here's a sort of in quotes version of our theorem. So this resolvent family exists. We claim a custom algebra of pseudo-differential operators, and in some sense, the limit as h goes to 0 of the Witten differential here, or of the resolvent of the Witten Laplacian, is this object. It's a natural Laplacian on the critical set, twisted by the orientation normal of the negative direction. So the limit of this resolvent is supposed to be a resolvent of a Laplacian acting on the critical set. So let me be a little bit more precise in this next slide. So given a without explicitly defining it, combine the two case lines. So we're going to consider a generalized Morse-Bott function. Well, basically, this is really kind of for the analytical convenience of being able to treat the Morse-Bott case and the generalized Morse case together. If you know of a nice application for generalized Morse-Bott functions, we would be happy to hear it. We're not explicitly aware of it. But so if my function has degenerate or non-degenerate critical submanifolds, then we can still form this Witten Laplacian, and the claim is that this resolvent family exists in an algebra of pseudo-differential operators, and it really is an algebra. For the experts, this is a small calculus, so you can always compose here. And these are operators on a space where, really sort of morally speaking, the space is m times the parameter space for h. We're sort of putting the parameter into the geometry and then we're resolving the singularity by blow-up, and I'll describe that more in a second. And this statement about the limit is really saying that there's a particular normal operator of this resolvent at one of the boundary faces of this manifold at h equals 0, and the normal operator of this resolvent is a resolvent of this type. And moreover, I want to point out that here, only the non-degenerate critical sets are appearing here. Any sets which have degenerate critical behavior are not shown. But just so a direct consequence of this theorem is we have sort of a spectrum as h goes to 0. So in this direction, this is the lambda current direction. So it's non-negative. A lot of stuff can be happening as we go down to 0, but the limiting spectrum is the spectrum of essentially, is the spectrum of the Laplacian on these non-degenerate critical sets. And in particular, the small eigenvalues are exactly the things which are going to 0 here. And that's the 0 eigenvalues of this operator, which is to say harmonic sections of the harmonic forms with respect to this operator, which again is to say the cohomology. So the space of small eigenforms here is exactly identified with the cohomology of the non-degenerate critical set, possibly to this normal. And there's a shift in the index. It's the correct shift that is not completely obvious from the statement of this theorem, but comes out. So we can also see, if you're interested in the large or medium-large asymptotics just by rescaling the spectral parameter, and there's sort of a similar normal operator that shows up, and principle you can compute exactly what the limiting spectrum is in those two asymptotic cases as well. So let me give you some idea of the proof here, just briefly. So if you write out this operator explicitly, you get the ordinary Hodge Laplacian. Then this is the Lie derivative by the vector field, which is dual to df, plus the adjoint of that operator. And so in fact, you might think this is a first order operator. It turns out to be a zeroth order operator. That's multiplied by h to the minus 1, and then h to the minus 2 times df squared. So now, you'd like to do this as a semi-classical problem. And in order to do that, I'd like to see h squared times the Laplacian here. So if you multiply by h squared, you get a semi-classical operator. With a semi-classical symbol, c squared plus df squared. So if you aren't familiar with semi-classical analysis, let me give you the two-line definition here. The semi-classical differential operators are essentially differential operators where we consider sort of homogeneous terms where there's h's are paired with derivatives, and the coefficients may depend on h. And in this sense, the semi-classical symbol is what you get when you set h equals 0 and formally replace h dx by essentially a cotangent variable. But note that, so in contrast to the principal symbol, if you're used to thinking about the principal symbol for microlocal analysis, I'm actually taking, this includes all orders here, so not just the top order. But in that sense, so I have h squared times the second order operator here, h to the 0 times the 0th operator here, and then these two terms are lower order because this is 0th order times h, so this h is really, in the coefficient here, when you set equals 0 disappears. So what's the idea here? We've got sort of a non-commutative algebra of differential operators here. This is sort of a function, so y is a commutative algebra. And the idea behind semi-classical analysis is that if you can invert this semi-classical symbol here, if this were everywhere invertible, then that would say in particular that we could invert this operator modulo error terms of order h, and then those are easily improved with error terms over h infinity, and then an exact inverse for small, which you can remove the errors entirely for small. So of course it's not everywhere invertible. It fails to be invertible exactly over the critical set, right? Because this thing might vanish, and then c is 0 is not invertible. So that failure is exactly what's responsible for the small eigenvalues, because if it were invertible, we'd be able to construct a result exactly. There would be no spectrum, no small spectrum. So the idea here is we adapt the sort of microlocal or semi-classical machinery to capture what I claim is the natural rescaling of the problem at the critical set at h equals 0. And let's see, I think I'm going to go a little bit quickly through this next bit, sort of getting details, and I want to get into the next one. So I claim that you can do just an explicit coordinate commutation allows you to see very directly what's going on here. Basically, so if we have product coordinates, just everything is a product. So the x represents the degenerate direction, and y's represent the non-degenerate directions of my Morse function. The critical set is therefore x equals y equals 0, and the z are coordinates in my critical set. And suppose that my metric is such that everything just splits exactly, so I just have the sum of the three Laplacians in these different directions. Just rename the terms here. So I claim that if you change variables here, in particular look at x over h to the 1/3, y over h to the 1/2, and then what I call h bar h to the 1/6. So I'm sorry if you're a physicist and you're offended by that, but h bar is not h to the 1/6. Then you get the operator breaks down like this. So there's these sort of three different operators that are now acting separately in the different directions according to different orders in this h bar variable. And so the separation of these operators in different orders in H is, as they say in software engineering, it's a feature rather than a bug. This actually makes the analysis a lot easier in our setting. One of the sort of features of doing this. The idea then is you want to invert this in formal power series. So there the operators again. The top order is essentially a simple harmonic oscillator. There's a shift term that causes this not to be invertible everywhere. It has a null space. So you can't invert it at the first order, so now you want to look at the next order term acting on the null space of the first order thing. Well, this is just an ODE, and you can actually see that this hasn't it has an L2 inverse, you can see fairly explicitly. So if this term is present, this is the term coming from having a degenerate critical point, then I can invert this operator. And so we see that there's sort of no small or medium eigenvalues if this critical set is degenerate. On the other hand, if there are no critical set is non-degenerate, so there's no x and no t, then that middle term is not there. I can explicitly tell you what the null space of this operator looks like. It looks essentially like a Gaussian, the ground state of the central harmonic oscillator, times wedge product of s variables, where these are exactly the s variables that span the normal, the negative normal direction. And so in particular, this is a basis for why the orientation bundle of n minus is coming up. And then forms along the critical set. And then, we want to look at this thing acting on the null space, and so that's the Laplacian on the critical set acting on essentially shifted forms on the critical set, twisted by this orientation. And so that's where we get this limit as h goes to 0 over degenerate critical, on non-degenerate critical space. The geometric setup is this. So I said we start with this space. We do a blow-up at the critical set at h equals 0. It's actually an inhomogeneous blow-up that corresponds to the rescaling that I mentioned in the coordinates. So there's new boundary phases here. We call this the critical phase, and the semi-classical phase here. I treat the problem semi-classically here, and then essentially the point of doing this is we have basically an invariant, geometrically invariant way of doing that explicit computation that I just did in global coordinates. So essentially the restriction of operators in these spaces are what I mean by the normal operators. So the big setup here is to just construct the pseudo-differential operator algebra associated with this. So it involves constructing a space on which Schwartz kernels and these things are going to live. It's sort of a blown-up version of this, and they compose on a blown-up version of this space. And there's, I claim, an invariant version of the coordinate computation that is not much more difficult, which mostly said it. One feature of doing the blow-up of the critical set at h equals 0 is you can actually see that these small forms are concentrating at h equals 0 to essentially Gaussians along this, on the front face of this blow-up. And so if you think about blowing them down, they're exactly delta-type conormal distributions on the critical set. So one way to sort of view what we're doing by blowing this space up is it's a space that resolves the delta-type singularity that the eigenforms have when h equals 0. All right, so in the minutes that remain, I want to talk a little bit about the Morse-Snell complex. So whereas the Morse inequalities, as I was saying, are sort of like the information you can extract from a chain complex if you don't have the differential, sort of the best you can do. But also, you'd like to say that you'd like to do better if you know something about the differential. So there's something called Morse homology, which was historically it was known probably in some form as Codimensional, but rediscovered again by Witten. So again, in just a classical case, just picture a Morse function with non-degenerate critical points. Using a Riemannian metric, you could look at the flow along the negative gradient, so the vector field. So the gradient of f gives you a vector field. Take the negative gradient of f, and you can look at the flow on the flow on a manifold defined by that vector field. So I'm going to call that phi t. So for a particular critical point, you can define the stable and unstable submanifolds. So if Q is a critical point, if P is a critical point, the stable submanifold based at P is the set of points that are limiting the P under this flow. So as T goes to infinity, it limits to P. The unstable submanifold of P is the set of points that are limiting to P as T goes to minus infinity. So in some sense, they're sort of coming from P in the past, and the stable submanifold is the set of points going to P in the future. So now, for a generic metric, it turns out that the intersections for different critical points of the unstable submanifold of one of the critical points and the stable submanifold of the other critical points are transversal intersections. So this is some condition, but it turns out that it's realized for a dense set of metrics on the manifold. So you can assume that this holds. Let me just put up the picture of the hot dog again. So for instance, the critical point downstairs, this is entirely stable. The stable submanifold is almost the whole thing. It's the whole thing, but for the line that connects these top two critical points. So one thing I didn't say, these stable and unstable submanifolds are always open cells in the manifold. They're smooth submanifolds, contractible, diffeomorphic to an open cell. So the stable and unstable manifolds here, the unstable manifold are these lines going down to the bottom critical point. The unstable submanifold are these directions here, the line that's going up to these critical points at the top. And the unstable manifolds of the critical points at the top are these sort of end caps. You take the whole Q-form here up until you get to this ring. So in particular, if you've got this transversality satisfied, if two critical points differ by, if their indices differ by 1, it turns out that this intersection is a one-dimensional submanifold and has finitely many components. And again, you want to think of intersections here as sort of gradient trajectories, things that are going from P to Q if the critical points differ by 1. So for such a gradient trajectory, it's possible to associate a plus or minus sign essentially by comparing orientations of the unstable submanifolds at P and Q. And then if you sum over the finite number of trajectories that connect P to Q, that gives you an integer. An equivalent version of this is this integer is the homological intersection number of the unstable and stable spheres of P. Well, unstable sphere of P and stable sphere of Q. I can define those, but they're essentially what you get by flowing out the sphere in these cells. So it turns out that if you just take CK to be the free abelian group generated by critical points of index K, that these form a chain complex. So this is the fundamental result of Morse homology, is that this forms a chain complex where the differential, so going from critical point of index P to critical point P to critical points of index 1 less than P, the differential is just given by these integers. And moreover, the homology of this chain complex recovers the integer homology of the M. So the cohomological sort of Witten version of this was proven by Helfer-Schusteren in the same paper that I mentioned earlier, and bismuth, and again, the same paper that I mentioned earlier. So at a cohomological level, you could say that, the desired complex is really just this. We have the chain complex consisting of small eigenforms, and then what's the differential? Well, it's the Witten differential, right? That is the chain complex that's computing the cohomology. We're sort of throwing away the information coming from the differential when we look at the Morse inequalities, but now we'd like to the challenge here is to come up with, to relate this to the Morse-Smale differential, which is just defined using sort of topological information. I'd like to relate the Witten differential to the Morse-Smale differential, and this is what Hofer, Schuster, and Bismuth do. So we believe that we have a good proof of this result, at least in the Morse case, and possibly the generalized Morse case. And it's an interesting question if you can sort of say something about the Morse Bot case, if you could actually get a sort of some description of the boundary operator, the differential there, some topological version of that would be very interesting as well. This is sort of work in progress, nothing's been written down, but it looks promising. So let me give you a quick version of how this goes. So the manifold has a stratification by unstable manifolds of critical points of increasing index. So if you take closures of unstable manifolds, so I claim that it forms a nice, well, actually I don't claim it forms a nice stratification. This is always true. M is always stratified by unstable manifolds. But under this transversality condition, and plus maybe a little bit more sort of normal form condition near the critical points, the stratification is smooth in the sense that Rafe mentioned earlier today. And so something that you can do with a smooth stratification is iteratively blow up the strata. You obtain a manifold with corners that has what's called an iterated vibration structure, which I won't define. But it's basically the package of information that tells you how the boundary faces fiber over base spaces. And the base spaces themselves are manifolds with corners which have iterated vibration structure. And the metric that you get under these conditions we claim is an iterated incomplete edge. So each component of this iterated vibration structure is a compactification of some unstable manifold for a unique critical point P. And so therefore it's contractible. It's just a compactification of this open cell. Its boundary faces fiber over other components that correspond to other points of smaller index. So there's a complex of forms on this blown-up manifold with boundary conditions that essentially say that recover the original complex of forms on M. It's essentially just the data that you can put on this that says that I blew up M to get here. And we claim that F lifts to a Morse Bot function. So because you have this vibration structure over the boundaries, if the boundary faces have the vibrations are non-trivial. So if the vibrations have fibers which are not just one-dimensional, then F is going to lift that. So the Morse Bot singularity is exactly as I mentioned before, rather than just Morse critical points. And then we claim that now you can run Witten deformation on this resolved manifold. And then it turns out that each component of the iterated vibration structure, which is a manifold of dimension k, there's a unique small k-form in its interior corresponding to this critical point. So it's a manifold of dimension k with some unique k-form on it, so that gives an orientation of this piece, and therefore induces an orientation on the boundary faces. And the boundary faces, again, as I said, are related to critical points of smaller index. So as before, the Witten differential is conjugate to the ordinary differential. And then just by using Stokes' theorem, you can reduce the computation of the Witten differential to a comparison of the orientations, which is exactly what you would expect to be getting from the Morse-Smale differential. So that's the outline of the argument here. And then for the finale, let me just run through sort of a proof-by-picture here. So here's our hot dog, and now I want to show you what it looks like to resolve this stratification by blow-ups. So first, I'm going to blow up the highest depth stratum, which is the critical point of index 0 at the bottom. So blow-up of that gives me a boundary face here, which is a circle now that has fibers over the point. Now the next stratum is this arc here, the unstable manifold of the critical point at index 1. And so if I blow that up, well, it's a codimension 1 thing. So blow-up is just sort of separating this manifold into 2 components with new boundary faces here. And then I put this thing in here because this is a component of the iterative fibration structure. So these boundary faces we're thinking of them as fibering over this middle piece. Of course, the fibration is trivial. It's just a matter. But the idea is that these 2 pieces, since they fiber over the same space, they're sort of related. They're coming from the same piece. So this is what my resolution looks like. Let me just flatten it out. So we have two components like this. So the critical points are now here. So there's going to be a unique small 2 form concentrating to a delta function here, a unique small 2 form concentrating to a delta function here, a unique small 1 form that's concentrating to a delta function there, and that therefore is associated to something living here and here by the fibration of these boundary faces over this side. And a unique small 0 form, just the constants coming from this point. And again, so the boundary of this thing are these 2 points, they map there, and then these dark lines on these 2-dimensional pieces, they also map to this, that was the original index 0. So now if you take orientations given to you by these small forms, and you compare the induced orientations to the boundaries, well, okay, so let's start here. So I have an orientation here, so that induces a plus and minus, the boundaries there. So what that's telling you is essentially that the differential going from here to here, so from the 0 piece to the 1 piece should be trivial because I have a plus 1, minus 1. So that cancels out, 0. The orientations here, so this one agrees with this orientation. So if I think of this as just mapping to the right, this orientation agrees with this orientation is the one that agrees with this, which disagrees with that. So I read off that here's my chain complex that I gave in this. So there's a copy of R, which is spanned by guys over here, copy of R, spanned by guys over here, and then 2 things living here and here. The differential, as I said, is 0 here, and this one maps to Z minus Z. So if you take the homology of that, you get surprise the homology of this. So, it must be true. All right, so thank you.
For classical Morse function, we had this whole argument about tunneling, right, between wells and then it really becomes a one-dimensional quantum mechanics problem, and you get your corrections and you say, aha, we got this zeros exactly where you got the differential line. But it seems to be an awful lot more complicated if you've got a Morse spot function. Can you say anything about what happens?
Yeah, the short answer is that the complex, again, is the Witten differential. So, but the challenge is, can you come up with some kind of topological description of that? And just sort of playing around with this, we've done some sort of examples of Morse spot functions, and it seems like, maybe there's something that you can say. I can't sort of tell you what the conditions are, or exactly what the statements are yet, but we hope that maybe under some conditions there might be something that you can say about the complex, some kind of topological description of the complex. Our description is a little bit different than Witten's, as you point out, and that's the same. So the Helfer-Schusterman proof is basically what you said. Basically, Witten's proof made rigorous using semi-classical analysis. It looks at sort of tunneling solutions, WKB solutions that are concentrating essentially on so the gradient trajectory here, for instance, between this critical point index 2 and the critical point index 1 is some line here. So the problem is somehow that you really lose the information about the differential when h goes to 0, because so what the argument is that things are concentrating here and here sort of exponentially fast, and they're also they're vanishing exponentially, therefore outside. In particular, they're vanishing exponentially along this gradient trajectory, but somehow they're vanishing like less exponentially along the gradient trajectory than away from the gradient trajectory. But if you're taking the limit as h goes to 0, mu0, so you sort of lose that information. So, I mean, it's not entirely clear to us how to get Witten's explicit description along the gradient trajectory out of this. This is more sort of aligning with the Snail decomposition of comparing orientations along. But I mean, there's certainly a lot of interesting questions there.